some degree, picks up where we left off, talking about intermolecular forces, and more specifically about how chemicals will interact with each other because of those intermolecular forces. Okay? Let's think about some ideas first. Let's start off thinking about mixing. If we take two compounds, separated, these don't have to be compounds, they could be elements, right? Gaseous phase elements or something like that. Separated by a panel, and then we remove the panel, the mixing will begin. Mixing will begin. The degree of mixing, though, will depend on how similar their intermolecular forces are. Okay, we know that water and oil, for example, don't mix, and we know that that is because of the different kinds of intermolecular forces. And let's see, I can't remember where we left off, but I'll give this to, well, I think I'll give it to Robert anyway. Robert, what do you think? What are the intermolecular forces that water has going for it?
Polar. So, I mean, anything that.
Whoops, I'm on mute. Let me.
Anything that is, or any solute, I guess, that is also polar is going to dissolve really well with it, just like any non-polar solution is going to dissolve, or solute is going to dissolve with any non-polar solution.
Right. Okay. Very good. So, what's that?
I was just gonna say, but the hydrogen bonds and just its high polarity is what makes it.
Those are the intermolecular forces it has, right?
Right. Yeah.
Right. And Sarah, what about oil? What are the intermolecular forces that are predominantly involved in oil?
Mostly London dispersion forces.
That's right, London dispersion forces. Okay, very good. So we have to have similar intermolecular forces for compounds to react with each other. Okay, or not react, but mix with each other. Okay, here is a compound, benzene and ethanol. And we can look at ethanol. Camille, what kind of intermolecular forces, based on the structure of ethanol here, do you think ethanol would like to have?
I honestly don't know. I'm sorry.
Okay, so what we're doing here is we're looking at ethanol, and we're looking to see how this molecule of ethanol would interact with another molecule of ethanol. Do you remember what these little doodads here with the minus sign and the positive sign mean, Camille?
I missed the last lecture.
Okay, these are the partial negative and partial positive signs, which are showing us that a dipole exists here. And there's also something special about this dipole, Brielle. What's special about this dipole?
It has a hydrogen bond between the oxygen and hydrogen.
Yes, it has a hydrogen being bonded to one of the big three, right? Which are nitrogen, oxygen, or fluorine. And so because we have oxygen bound to a hydrogen, that would mean that this compound would be able to hydrogen bond with its neighbor, ethanol. And that is a relatively strong intermolecular force. It's a dipole, but it's a souped up dipole, right? Okay, so ethanol, we have dipole, hydrogen bond, and London intermolecular forces, right? London forces. Now, if we look at benzene here, Jace, can you give us an insight what you're feeling on benzene? What kind of intermolecular forces are we going to have here?
we're only going to have London because there's only carbons and hydrogen, so that it's going to be a non-polar molecule, and so we're only going to have London dispersion forces.
That's right. Very good. Only going to have London dispersion forces. And you didn't mention the symmetry, but we also have a very symmetrical compound here. Very good. So these compounds don't mix, and you can see them poured into a beaker here. Our water on the bottom and our hydrocarbon on top. And we always can remember also that hydrocarbons like to be, sorry, not water on the bottom, ethanol on the bottom, hydrocarbon on top. Okay. So we have here some compounds: acetic acid, carbon disulfide, water, ammonia. All right. And we'd like to think about which one of these three here are miscible with the water: acetic acid, carbon disulfide, ammonia. And when we do this, what we're looking for is we kind of need to know the structure of the compound. And, ammonia here and carbon disulfide are drawn a certain way, but it might be tricky for us to kind of see. I'm going to let you guys break into groups and try to find out if you can answer this question: which of these three are miscible with the water? Okay.
Okay, so we think acetic acid is miscible in water.
Why?
Because it looks like it is polar.
What are the red spheres,
No.
Okay, here's water.
Oh, so they would be oxygen.
Oxygen, that's right. And the white spheres here, the small white ones?
They would be hydrogen.
So here we have oxygen and hydrogen bound together asymmetrically, right? So what does that tell us?
That it's polar.
It's polar, and we're going to have what kind of intermolecular interaction here?
A hydrogen bonding.
Yeah, hydrogen bonding. Very good. So that's how we can tell that acetic acid is going to want to interact with water. What did you decide about carbon disulfide?
So we thought that it was not miscible in water because it looks pretty symmetric, which means it's likely nonpolar.
All right. So we do have to make sure that, one, we know what carbon disulfide means as CS2, if the picture isn't good enough for us or if they don't provide it. And two, we also have to make sure we can look at the picture and, we can't rely on the picture necessarily. We always have to be comfortable with drawing our own Lewis dot structures. And if we add them all up, add everything up, we see that this is our Lewis dot structure. Therefore, no really strong polar bonds and no asymmetry. It's very symmetrical. So those are the reasons why we know that it will only have London dispersion forces. Very good. What did you guys think of in terms of ammonia, Sarah?
So ammonia has an N in the middle.
Mm-hmm.
So that means it has hydrogen bonding. And so does water. So we thought they were miscible in water. It
Okay.
was.
So what is the shape of ammonia? Do you remember, Sarah?
Is it trigonal planar, maybe?
Okay. That is a good guess because that's what it looks like. That's what it looks like. It looks like it's trigonal planar. But again, just like with the CS2, especially if, we get some weird drawing like this and we can't tell exactly what it is, we want to be able to draw the Lewis dot structure for our compound. So once we do that, and H, right, add up our electrons, we're going to find that we have 2 more electrons that go on that nitrogen. This is a hard one, Sarah. Do you remember now what kind of a shape this compound is?
I definitely don't remember.
Okay. We have 4 regions of electron density. That means that those 4 regions are going to take a tetrahedral shape. 4 regions take tetrahedral shape, but one of them is non-bonding. So what's left is, if I can try to draw a good tetrahedral, we have one coming out toward us like that, one going kind of off into the back, and then one going into the plane, and then one going up, right? So it's kind of like a little pyramid, right? That's what the whole thing looks like. But then when these are non-bonding electrons, then all that's left is this shallow pyramid, which is a trigonal pyramid. So this is a trigonal pyramid, and it's asymmetric. Asymmetric. It is not symmetrical because you have this non-bonding region on top. Therefore, that's how we know that ammonia will dissolve with water, because it's asymmetry, and that nitrogen-hydrogen bond there will allow it to hydrogen bond as well. Okay, so acetic acid, miscible in water, and ammonia, miscible in water as well. I need to open, I got the wrong one here. I gotta open. All right, there we go. Okay. Alyssa. No, Brielle. Brielle's turn. Brielle, what do you think? Want to take a look at this question here and answer it in about 9 seconds? Everybody else try to look at it too. When questions are like this and it becomes more difficult to kind of imagine in our minds maybe the structure of the compound, it takes a little bit of time and you have to get better at that. Any ideas, Brielle? What do you think?
I'm guessing C because it looks like it could have a hydrogen bond.
That's right. Very good. So this C6H6, no oxygens. It's going to be a symmetrical compound. This one here, it's easy to see that it's symmetrical. Butane is what it's called, butane gas. That's what's in lighter fluid, or sorry, cigarette lighters, butane. So it's the one that has the oxygen and the hydrogen bound to each other, and specifically on the end of the compound. Very good. Now, we've seen this multiple times before, the way ions dissolve in water, right? Ions can be surrounded by water molecules, and you can get a significant interaction from the positive sides of water molecules with the negative ion and negative sides of water molecules with positive ions, right? Solubility, remember that word? We have a solubility table that we've talked about in 105, right? If the interaction between the positive and negative ions is stronger than this intermolecular interaction between water and the ions, then you won't get a soluble compound, right? You only get a soluble compound when the resulting intermolecular interaction between the ions and the water is stronger than the interaction between the cation and anion in the ionic compound. Interaction we can call an ion dipole interaction, right? An ion dipole, because it's the dipole on water which results in the polarity of the atom or the molecule, and that's why it can surround and entertain these ions. All right, sugar, something that we know is soluble in water, not an ionic compound, but the intermolecular interactions between water and sugar are similar enough that sugar will dissolve in water as well. Now, when this occurs, when you get
there aren't too many armies. You know, you gotta be.
When you get a solid dissolving in water, sometimes you can get a release in heat energy or a change in heat energy.